Hello everyone. In some series of lectures, I am going to make some practice with you depending on the stage of the lectures that we are located at, and especially as we have had already porosity, permeability, Darcy's law, single phase flow in porous medium, especially sand pack, potential, K as bundle of tube theory, and Kalman-Kozeny, etc. And especially also last lecture, which was about upscaling. I found it the right place now to do a bit of reflection and solve some practical equations, problems for you, so that we make a kind of question-based revision and see what type of problems we can also solve, knowing all the past knowledge. So the first topic that we discussed as the static property of porous medium was porosity. So I'm going to make a few questions for you related to porosity calculation so that we can practice this. So imagine I have a rock, a porous rock, and I want to find the porosity of this. Now I am given this information. This is a sandstone rock which has the density of 2,500 kilogram per cubic meter. That's the density of the typical sandstone, 2.2 to 2.7, 2.9 gram per cubic centimeter, or 2,500-ish, for example, kilogram per cubic meter. And now imagine that I know now the density of this, and I am going to be given also the weight of this rock. So assume that the weight of this rock, so the mass of it, is 1 kilogram. The mass of this rock is 1 kilogram. So my question is, let me just write mass a bit more beautifully. So mass is 1 kilogram. Knowing the mass of the rock and the density of the solid grain, I can find what would be the volume of the material if it was 100% solid with no pore space, right? Now here I am also given the volume of the bulk porous material as 500 cubic centimeter as the volume that it has. Great. So I'm given the question of what's the porosity. Let's consider if it was 100% solid, what would have been the volume of the pure solid, no porosity? Density is mass per volume. So volume is mass per density. 1 kilogram divided by 2,500 kilogram per cubic meter is my volume, which is 1 over 2,500 cubic meter. So I know 4 times 25 is 100, so 4, and that becomes 100, so it becomes 10, it becomes 1,000. So if I multiply numerator and denominator by 4, I get the value that is 4 divided by 25 becomes 100, 10,000. That is my volume of the pure solid, which is 4, 10 minus 4 cubic meter. Now 1 centimeter is 10 minus 2 meter, therefore this is also equal 400 centimeter cubic. Centimeter is 10 minus 2 to the power 3 is minus 6. Here I have minus 4, so I get 2 more here. So that's the volume of the only if it was pure solid, no porosity. But I know the real volume is 500 cubic centimeter, I'm sorry. So therefore, the porosity, which is the volume fraction of pore space over the total bulk volume, is 400 cubic centimeter and 500. What would be the volume of the pore space? The difference, right? 500 minus 400. So it would be 100 cubic centimeter, sorry. Total bulk volume would be 500 cubic centimeter. That's the total bulk volume. So if I do this, 1 over 5 is 20%. So porosity of my material, my porous system is 0.2. Or I can write it as 20%. So the pure solid could have taken smaller space, but the total now porous rock is 500 cubic centimeter. So therefore, 100 cubic centimeter is the void space here, and that divided by total bulk volume is 20% porosity. Fabulous. Now let's do another way of porosity calculation. Imagine I'm given a rock, which is again 1 kilogram. I'm sorry, this is math. Mass of it. Mass of the rock is 1 kilogram if it is dry. Right? Now, I make the rock wet by putting water in it. So when I make it wet, the wet rock has the mass of 1.1 kilogram. My question is, what is the volume of the porous space in this rock? Well, the dry rock is 1 kilogram, the wet rock is 1.1 kilogram after I fully penetrated with water. Therefore, the mass of water in my system, in my pore space, is 0.1 kilogram. I know density of water is approximately 1,000 kilogram per cubic meter. Therefore, the volume of the pore space, which is the space that water could penetrate, is again mass per density, which is 0.1 divided by 1,000. This is density in the denominator, and the 0.1 is the mass of the water. And that becomes also 10 to the power minus 4 cubic meter, because the density is in kilogram per cubic meter, and the mass is also kilogram. So I know that the volume of the pore is this. Now, if I knew that the volume of my rock, my porous rock, if it was 500 cubic centimeter, which is 5, this is 10 minus 6 minus 4, so 10 minus 4 cubic meter, then the porosity of my rock, if I would be given this value, that the volume of the bulk is 500 cubic centimeter, knowing that the void volume is 10 minus 4, I know here that my porosity is volume of the pore over the total bulk volume, and that means that my volume of the pore is 10 minus 4 cubic meter. You need to be careful with the dimensions here, right? Use all the same SI unit. 5, 10 minus 4, which will be then 1 over 5. These two cancel each other, so therefore it will be 2 or 20%. So these are two different ways to calculate porosity, right? There are other measures that I did, like gas law, etc., but let me just move on to the next step of our practice. So that was porosity for now. Now I go to permeability. Remember, permeability with Kalman-Kozeny was 1 over 150 grain size to the power 2, diameter to the power 2, porosity cubic, 1 minus porosity to the power 2. If I'm given the grain size diameter, for example, if I'm given dP for a porous material like A is 200 micrometer, and its porosity, for example, to be 1/4 or 1/5, let's call it 1/5, which is the same as the sample we practiced before, I can find an estimation of the permeability of that sample A to be 1/150 times grain size diameter to the power 2, 200 micrometer. Micro is 10 to the power minus 6. 200, 2 orders of magnitude will be reduced here. So it will be 2 times 10 minus 4 meter is the diameter in metric, in SI unit. And therefore, that to the power 2 times porosity, which is 0.2, to the power 3, 1 minus 0.2, which is 0.8, to the power 2. This will be the permeability in cubic, in square meter, right? And then you can do the simplification of the mathematics for it if you like to have, for example, let me try, but do not expect me to do all the math all the time when I do practice with you, but 2 to the power 2 is 4, so I get 4 here. 10 to minus 4 to the power 2 is 10 to the power minus 8. Then 0.2 to the power 3, I have 2 to the power 3, which is 8. And then 10 minus 1 to the power 3 is 10 minus 3. Then I have 0.8 to the power 2, it's 64. Then 10 minus 1 to the power 2, which is minus 2. And that is cubic meter. Sorry, square meter. Meter square. And then you can do, please, the mathematics, and don't expect me to do this now in here for you. You can just take all the things that you want, like minus 2 here, makes this minus 3 to be minus 1, and then you can extremely simply find what the value here would be. This is 1, this is 8, for example, and then 8 will be 2. It takes this out, so you get 2 divided by, I can't stop doing the math, 2 divided by 150, and then I have 10 minus 8 here, times 10 minus 8, 10 minus 8, and then there is one negative sign in here, so it will be 10 minus 9, so that is 10 minus 9 square meter. And then you can translate it to Darcy, which is 10 minus 12, so you get 3 digits in the denominator and then get rid of minus 9 and make it Darcy, and then you do your business, right? I don't want to do all the way at the end and then later I find that I have mistakenly put minus 8 or 9 and then I just will have bad time to have it again recorded again and again. I'm sure you can do the math here as well, very well. Now, one question I have is, for example, you may be asked this. I have another reservoir, another porous rock, in which the grain size for sample B is twice the grain size of sample A. And I'm asked to, and the porosities are the same. And I'm asked to study the relationship between the permeabilities. Because permeability is proportional to the grain size diameter, to the power 2, I can then easily say that the permeability of sample B must be 4 times the permeability of sample A, because it's proportional to the grain size to the power 2. So I can relate these as well. Grain size twice big, permeability 4 times bigger. Fantastic. One great example that I can do is when I have a reservoir like this, a 1D reservoir, which is, for example, split into 2 sections of L. I put the left into P left and the right side to P right. I am asked to plot pressure for 2 scenarios. Scenario A, which is scenario A, which is plot the pressure. So plot the pressure for the case that Ka and Kb are equal. This is section A This is section B. And also plot the case for which Ka is, for example, 2 times Kb. So, how do we deal with this question? Since it's a 1D flow, incompressible, divergence of velocity is 0. Therefore, velocity is constant, CTE, constant, which means velocity, which is K over viscosity, delta P over L, for section A is equal the K over viscosity, delta P over L for section B. Viscosity is the same, and what else is the same, my friends? So here length, this is L and L. Length doesn't have to be equal. In this case, simple case, I am giving a splitting into half exactly. So L of A and L of B are equal. Just for this case, you can have it different. So I am going to also cancel this, which then gives me the relationship that the K of A, the pressure drop in A, is equal K in B, pressure drop in B. So if Ka is equal to Kb, then the delta Pa and delta Pb are equal. So delta P in A is equal pressure drop in B. If Ka is 2 times Kb, so I put 2 times Kb here, Kb and Kb cancel each other, then I find that 2 times of the pressure drop in A section is the pressure drop in B section. Because instead of Ka, I wrote 2 times Kb. So case A is nothing else than just simply a linear homogeneous pressure drop. That's the Ka, the yellow one. Now with the purple marker, I am going to plot the case B. Case B says delta P in section B is twice of the pressure drop of section A. So it means that at this section, there will be a change of the slope of the pressure. Here it is a smaller drop. Here is bigger drop. The slope here is 2 times of the slope here. So this is a slope A. This is a slope in cross-section B, which is twice of the other slope. So that will be 2 times of the slope A. So because the permeability of A is higher than permeability in B. When permeability is higher, pressure drop is lower. High permeability means lower pressure drop, so the multiplication is constant. In a way, you need little pressure drop to cause the same flux as for the nonlinear, the low perm region. So slope B is twice, or pressure drop in B is 2 times pressure drop in A section when the permeability of B is half of the permeability of A. In extreme case, when Ka is very, very, very significantly higher than the section B, the pressure drop in the A section would be almost 0 because there is no resistance in front of it. So Ka times delta P in that section is the same. If length of each section was not the same, so you had LA and LB, then you needed to keep L2. So you needed to write that Ka delta PA over length of A would be KB delta PB over length of B. And then you would have needed, for example, if length of B was twice big, you would consider that 2 factor here too. That's quite practical and quite interesting that with that simple stuff that we have had so far, it's not really simple, but I just was very much motivating you to consider it simple. But for what you already have studied, you see how many practical questions you can solve. Now, the last practice would be about upscaling. So, imagine I have a parallel domain like this. And there are two sections for simplicity. This is Ka, this is Kb, and that is delta Ya, the thickness of A, and this is delta Yb. Imagine I'm given a question of find effective permeability for this system if the flow is parallel to the layers, for the case that Ka is 2 times Kb and delta Ya is equal delta Yb, both equal to small h, for example. That's very easy. We say that effective permeability is arithmetic average, which is delta Ya over delta Ya plus B, which is total, times permeability A plus delta Yb over the delta Ya plus B Kb. And we know that both of them are all small h, so the total value is 2h and each of them is h. So simply saying, you will get to see that the average will be Ka plus Kb divided by 2. Ka is 2 times Kb because of the information given. So the effective permeability will be 2 plus 1, 3. 3 times over 2, which is 1.5 of Kb. 1.5 times of Kb. So between Kb and 2 Kb, it is 1.5 Kb. So it's exactly the midpoint. If I had normal to the flow, and that was Ka and Kb, and then I had length of each L equal, my K effective, imagine I would like to know the same K effective for A to be Ka to be 2 times Kb, and then the length of each are the same. So if this length is delta x of A and this is delta x of B, both are equal. Delta xa is equal delta xb equal L. The effective permeability here will be harmonic because they are normal to the flow, right? So then it will be L total, which is 2L, over L1 over K1, L1 over Ka, plus L2, which is again L, over Kb. We did that in the last lecture. That became K effective, became 2 Ka Kb divided by summation of A permeability and B permeability. Now put Ka to be 2 Kb. So imagine this is 2 times Kb for the same experiment that we did above for parallel flow. That becomes 2 times 2 is 4, so that becomes 4 Kb to the power 2 divided by 2 Kb plus Kb will be 3. That will be 3 Kb. So effective permeability for harmonic average, which is normal to the flow, will be 4 over 3 Kb instead of 1.5 Kb. That's why the harmonic average is now here 1.3 almost. This is 1.5 for the arithmetic average. That's why the harmonic average gives you an average closer to the smaller value. This is 1.3, this is 1.5. 3 over 2 is 1.5 Kb. While this is almost 1.3333 Kb. That's why the harmonic average gives you closer to the smaller value, not exactly at the center. And that's why when Ka or B is 0, the entire system would have effectively 0 permeability. I hope with these practices you actually got to do something more practical and tangible so that you can understand and make sure that you understood all the lectures we have had so far. I come back again with continuation of the lecture series.